Okay. Well, thank you for showing up. As I mentioned in my announcement, I did test positive for COVID, so I'm following CDC guidelines about isolating. Pascal has graciously allowed, if you're going to do the exam in person, Pascal will be doing it. He'll also be doing the Zoom session. He'll be monitoring that. So you can go and do that. I might try to jump into the Zoom session after my lab and the other class is complete, so I can't be two places at once. But I can't be live in person because of the whole, expectation of isolation. But hopefully it'll go reasonably well. We'll go from there. All right. So let's get started. We'll go through sort of the exam review. That seemed to work reasonably well last time. And then feel free to interrupt with any questions you may have. Hopefully people have seen this. It's been up there for a little while. But the key things about this, and the first topic is pole zero maps. And we actually spent a little bit of time last semester talking about pole zero maps. And pole zero maps are essentially a way of drawing where the poles and zeros are in the S domain. And they're not super useful for us if we're just looking at, a specific pole other than determining stability. So we know that if all poles are in the left-hand half plane, that's the key thing, all poles are in the left-hand half plane, then you know that your system is bibostable. I'm sorry, go ahead.
Oh, I'm sorry.
Oh, that's okay. If you have any pole, so it's any pole, not all, but any pole in the right-hand half plane, you have an unstable, unstable system. And then if you have any pole on the J omega axis, you are marginally stable. And the reason why you are marginally stable is because you need to know what the input is to make sure that your system remains stable. So a perfect example is if we have a pole at S equals 0, that's an actual integrator. And an integrator, if you hit it with a DC input, the DC input stays constant, but as you continue to integrate, it just keeps going higher and higher and higher until if time approaches infinity, then your integration approaches infinity as well. So that's why that system is considered marginally stable. So this is really focused though for finite poles. You can tell the stability looking at the finite poles. Poles, the infinite poles are zeros. So remember, we always have the same number of poles as we do zeros. If you don't have the same amount, then the difference is made up by the infinite poles or zeros. Your infinite poles, you don't usually plot those on the basic S plane because you don't always know if they're to the left or to the right. I usually will show them if the system is stable, plotting them to the left, but that's not always necessarily the case. So if you have any poles that are at S equals 0 or zeros, I should say at S equals 0, then you can change things a little bit in terms of your results. But that's the easiest way to do these is to do your pole zero map, show all the finite poles. And then if your system is stable, you can show any additional zeros at S equals infinity and show those sort of way out to the left of the real axis. We then move to first order system response. And first order system response means your pole has one energy storage device. It could be an inductor, it could be a capacitor, it could be a damper, it could be a mass. It really just depends on what type of system you're analyzing. So we always start with a time constant. So we've been doing this quite a while in circuit analysis. If you go back to DC circuit analysis, we developed the concept of a time constant, and we expanded that quite a bit in EET325, where we looked at the details of time constants and how those came to exist. And then once we have our time constant, we can actually use that to calculate rise time. So rise time is for a system to go from 10% of its value, of its final value, to 90% of its final value. The reason why we start at 10% is because we need to know that we actually started. The reason why we go up to 90% is to know that it just takes an infinite amount of time to get to 100%. So let's stop it at a reasonable value, call it 90%. And then in this semester, we're focused on settling time that is within plus or minus 2% of its final value. In a first order system, it's always going to be below. So it's always going to be a minus 2%, so below its steady state value, because a first order system cannot overshoot. But here are our three equations. They will change once we look at second order systems, but we will use the same concept of rise time and 2% settling time when we move over to second order systems, which is our next topic. Excuse me, I have to blow my nose because I apologize. Just give me one moment because I'm having a hard time breathing here. I'll be right back. Okay, apologize for that. Sheet here. Okay, hopefully you can still see the sheet that we're working at, which shows the second order system response. And the second order system response, we did a lot of work on that. And we looked at the different system types, mainly as it relates to the type of damping or how damped the system is. We looked at three cases where we had an overdamped, a critically damped, and an underdamped. And the underdamped case considered that there was no damping whatsoever. That's still considered underdamped. And if we did that, we could come up with a generic equation whose characteristic equation for that second order system is S squared plus 2 zeta omega sub n plus omega sub n squared. So this is the general form of that. And you can solve for your parameters if you have a characteristic equation by setting your characteristic equation equal to this generic form. And omega sub n is our natural frequency, and zeta is the damping ratio of our system. We also can expand that to do our damped frequency as a function of our natural frequency by multiplying that by 1 minus the square of zeta. If the system is underdamped, this is always going to be less than 1. And the reason why it has to be less than 1 is when you do your quadratic equation, what is within the square root has to be a negative number, so you can get that plus or minus j root that you need. If you have an underdamped system, then these equations are applicable. If it's an overdamped system, then you just got to go back to this equation where you look at whatever is going to give you the longest time constant and use this as your rise and your settling time, because an overdamped system is essentially two systems, two first order systems combined together. A critically damped system is the same, where you have two first order systems, but their time constants happen to be the same. So these equations only apply for an underdamped system. But in the first case, in first order system response, we can never have any overshoot. So we never had to worry about developing this equation, this percent overshoot equation. But here it is. This is probably the hardest equation to represent. The next equation is the peak time. So here's your equation, and I would just put these three equations here for forced order, and I would put these three equations here on your formula sheets so that you don't have to worry about them. Just include those on your formula sheets. They'll be pretty comfortable for you to go ahead and use those. Our peak time, so this is a different one. So again, we have to add this equation in here because our peak time essentially means that how long does it take to get to a peak? Well, we don't overshoot in our first order system case. We can have overshoot. So that's why we had to develop this additional equation. And then our settling time equation is 4 over pi omega sub n. So this is the same settling time we have over here. We just do it over here. We're not super worried about rise time because in a second order system, we always have overshoot. So it doesn't stop at 90%. It can continue to rise and exceed that value. So what we are more interested in is, okay, fine, what is the actual settling time? That's a more useful design characteristic. And that's essentially all the stuff on second order systems. Any questions on that? Okay, block diagram math. So what we learned is a couple of ways to simplify a system that has been converted into a block diagram. So our block diagram is shown this way. And we want to move things because we want to combine them and simplify our complex block diagram into a much more straightforward form where we have one feed forward gain and perhaps one feedback gain. So we can easily find either the closed loop transfer function or the open loop transfer function. And when we started looking at steady state errors, we started to see how using the open loop function was really helpful for us. We're also going to see that when we start looking at root locus. But here are the steps. If you've got two blocks in cascade, you simply multiply them. If you have two that are summed together, you add or subtract them together. If you're moving a pickoff point around a gain block, if you're moving it from left to right, you divide. If you're moving it from right to left, you're going to multiply by that same gain value. Over here, if we're moving a summing block, if we're moving that summing block, so essentially we're moving the summing block to the other side of the gain, we're going to simply go ahead and then multiply our input by that value of, over here. We have to multiply both inputs by that value of G. If we're going in the other direction, then we're going to go ahead and convert it in this other direction. So what we're really doing is we're always looking at, and this is what we just talked about in class, is moving a pickoff point or a summing junction around a gain block. So when you're doing your work and you're trying to figure these terms out or these parameters out, make sure that you say, I'm going to the left or the right of a gain block. So I'm moving my summing junction to the left and to the right of a gain block. I'm moving my pickoff point to the left or to the right of a gain block. I'm not moving my summing junction to the left or the right of a pickup point. That the math for that doesn't necessarily work. Okay, so that's what this is for. This last thing, which is an important one to simplify your work, moving around a block gain. Then we moved on to Ruth Horowitz, and Ruth Horowitz was really helpful to come up with. Excuse me. Ruth Horowitz was really helpful to come up with a way of analyzing a system and determining if we have any poles in the right-hand half plane. And not only will it tell us if we have any poles, it'll tell us a number of poles that are in the right-hand half plane. So when you do your Ruth Horowitz, you can go ahead and do that calculation. And what we talked about in class is if you have MATLAB or your calculator that can calculate the roots, then you wouldn't necessarily need Ruth Horowitz because it'll tell you exactly the roots and where they're located. So you can just count if how many that are in the right-hand half plane. The real power of the Ruth Horowitz is if you have a variable value of gain, a value of K that you can adjust or tweak, you can increase or decrease that value of K so that your system remains stable or becomes unstable. So doing the Ruth Horowitz approach really simplifies things and gives us the value of K values that we can do it. So here's the approach. Find the highest order S term. So this is just for our characteristic equation. Find the highest order S term. And then we're going to write our rows as the highest order S term all the way to S to the 0. Then we're going to develop those first two rows by alternating S terms. So if we have an S to the 5th, what goes in the first row is S to the 5th coefficient, S to the 3rd coefficient, and S to the 1 coefficient. And then we go to the second row, S to the 4th coefficient, S squared coefficient, and then the S to the 0 coefficient that goes in there. And then once we do that, we have to determine, using the determinant approach, we find the rest by doing the 1 over the value of the coefficient that we are looking for, or the element just above. And then we find the determinant of the vector, the matrix that is formed by the row directly above, the column directly above, and then the one just immediately to the right of the coefficient we're trying to do. Then we talked about two conditions where if our determinant terminates prematurely, means we don't already get down to the S to the 0. If we have 1, 0 at our first coefficient or in our first column, then we go ahead and substitute our value for E, which is a number that approaches 0, but it's not necessarily a 0. So we substitute our value of E, continue with our work, and then we check to see if that value approaches 0. Do we get any changes? If we have an entire row of zeros, and that's always going to happen on an odd row, so the S to the first, S cubed, et cetera, then we have to write the auxiliary equation. That auxiliary equation is when we move up one row. So if it's a row of zeros at S to the 1, our S squared row, we grab the coefficients from that, And then our auxiliary equation is that those coefficients times are multiplied by the terms or the S terms in the previous row. So if it's S squared, we're going to take the first coefficient, multiply that by S squared, and the second coefficient, and we're going to multiply that by S to the 0. So just like we did in the first two rows where we alternated S terms, not S terms, but alternated coefficients based on the multiples of S, we do the same thing for the auxiliary equation. Then we take the derivative of the auxiliary equation, and the coefficients that we end up with there are going to end up in the row of zeros. And then we continue from there. Now, the thing about this approach is, and again, if you read the book or the book that I'm referencing that I encourage you to use, it does say there can be some cases when you have this condition. The only cases I've ever seen is when your system is marginally stable. So remember, Ruth Horowitz only tells you if you have any poles in the right-hand half plane. It doesn't tell you if you have marginally stable. So you can complete your Ruth Horowitz approach and not have any poles in the right-hand half plane. But this case will tell you that you have a marginally stable system. You have poles on the J omega axis. Okay. And then once you have that, you can set your value, the variable gain value that you have, you can adjust that so that your system can remain stable. And that's pretty much all the new material that we covered for this exam. So here are some specific test questions. If I, excuse me, if I give you a characteristic equation, determine the number of poles in the right-hand half plane. If I give you a characteristic equation with adjustable parameters, specify the range of the parameters so the system gets stable. So the first two, A and B, you should start thinking about maybe doing Ruth Horowitz. For part C, if I give you a block diagram, specify parameters to meet design criteria. So you might have to do a little bit of block diagram math, but you might have a first order or a second order system where you're going to go ahead and have a value of K, and you need to define, if I've given you parameters to pick some values of K or, some other parameters, an A and a B coefficient, to go ahead and meet settling time, percent overshoot characteristics. That part D is to do some block diagram math to simplify a more complicated block diagram. And then the last one is if I give you a second order transfer function, find zeta, find omega sub n, find percent overshoot, find settling time, find peak time, that type of stuff would be the parameters that you would calculate. So that's all I had for that. Any questions on anything?
Hey, Paul.
Yes, sir.
Can you cover homework 6 suggested problem number 2, please?
Sure. Let me bring it up. Oh, that's in the wrong class. Sorry about that. It's in the wrong folder. This problem right here.
Yep.
Okay. All right, so it says we have the following block diagram. So we want to figure out gain that indicates we have less than 10% overshoot. So you know that our percent overshoot is our first equation is going to be equal to 10%. That equation is going to be equal to, let me bring that up over here. Let me just snip this and bring this into here. Oops, let's see if I can shrink this down a little bit. Okay, so that equation, the first thing you do is you're going to have a percent overshoot. 10% you're going to set that equal to here and solve this equation for zeta. Okay. That's the first step. Solve that equation for zeta. And we develop the equation and how to do that. I can't remember which class we do, but it's just a little bit of a mathematical process. You got to take the ln of both sides. Be careful about the negative sign because you can get yourself set up where you forget you have to change equalities. But essentially, once you do that, you're going to have a value of zeta. Okay. That's the first step. The next step is to solve for the closed loop transfer function, which is 25k over 1 plus, whoops, g of s squared plus 8s plus 25, all over 1 plus 25k over s squared plus 8s plus 25, which is equal to 25k all over s squared plus 8s plus 25 plus 25k, if I did that correctly. So now, I've got my value of zeta. So now all I really care about is my characteristic equation here. So s squared plus 8s plus, sorry, this is just a little messy, plus 8s plus 25 plus 25k equals, in standard form, s squared plus 2 zeta omega sub n s plus omega sub n squared. So my omega sub n squared is equal to 25 plus 25k. You have that. Now, you're going to solve. So you're going to solve for omega sub n by taking the square roots of both sides. Once you have that, 8 is going to be equal to 2 zeta omega sub n. So you know the value of zeta, you solve for it over here. You're going to substitute that into here, and that'll let you solve for your value of omega sub n. And then you can plug that in and solve for your value of k. So omega sub n is equal to zeta 4 divided by zeta. And then you're going to set that equal to the square root of 25 plus 25k, and then solve for k. And once you have your value of k, then your peak time and your settling time equations are going to be right here. Let's zoom in a little bit. That's it. That answer your question, Ethan?
Yeah, thank you.
Sure. Yeah, the part that's important on this one is, and it's kind of anytime you see a design parameter when you have a 10% overshoot, you always solve for zeta. And in this case, solving for zeta is really effective because it allows you to calculate omega sub n. So once you have zeta, you have omega sub n, then you just pull that value of k from there. Normally you solve for omega sub n first, but this one we don't actually have to solve for it. We can do it that way. Other questions?
Could we go over suggested problem number 2 on homework 7?
Sure. Bring it up. Okay, so given the characteristic equation, I'm going to go ahead and copy this into whiteboard. Whiteboard just seems to be a little bit nicer to work with. Okay, So this is a Ruth Horowitz, right? We have to do Ruth Horowitz. So the first thing we do is we identify the rows. So here's row S4, S3, S2, S1, and S0. Here are our rows. Now we're going to go ahead and start putting in our coefficients. We start off with the S to the fourth coefficient. Then we move to the S squared coefficient. And then we move to the S0 coefficient. There's our first row. Now we're going to go down to our second row and we're going to use the S cubed coefficient. And the S to the 1 coefficient. Now we're going to go ahead and solve for the parameter. So it is 1/6 times the determinant of 118, 6 K minus 12. So that's going to be equal to, let's put that over here. Let's call that A. So that's going to be equal to K minus 12 minus 6 times 18 is 108, I believe. All over 6. So that's equal to K minus 120 over 6. That's that first coefficient. Our B coefficient, so this is equal to A. Our B coefficient, because we're running out of space, I'll put it over here. So again, I'm solving for B, which is going to be over here. So I'm still using my first row. My second row, or we're using my first column. My second column is going to be the one just to the right of it. So my B term is 1/6 all over, or 1/6 times the determinant, 1/6 K and 0. So that's going to be equal to -6 over K times 1/6 is -K. All right, so now I'm going to go ahead. Oops, somebody say anything? I didn't quite hear. I'm sorry. Anybody say anything? I might have misheard. Okay. So C now is going to be equal to, so I'm going to be using this term here. So 1/K minus 120 over 6, which really becomes 6/K minus 120 times the determinant. So I have 6 and K minus 120 over 6. And then this is K minus 12. And oops, I'm sorry, I get the wrong. No, that's K. Yeah, I'm in the wrong spot. Sorry, guys. This here is K minus 120 over 6. And this is K minus 12 over minus K. So this is a little bit of a nightmare, but that's okay. So it's going to be equal to 6/K minus 120. And this is going to be equal to -K times 6 minus K minus 12, K minus 120 over 6. That whole thing is multiplied. That's our C term. D is equal to 0. We don't have to even calculate that. And then our last problem, our last one is D, which is over here. Our D term, we don't have to do any work. We could just say that it's that last coefficient. It's equal to 12. So now, what we need to do is we need to say K minus 120 has to be greater than 0 for my A term, and my C term. This is a bunch of work, but let's see, it's 6 times -6K minus K minus 12 times K minus 120 all over 6. And so that has to be greater than 0 or equal to 0 as well. So at this point, we do common denominator, 6 next, we can get rid of the 6. We don't even need that. We put this under common denominator. So this is negative 36K minus K minus 12. I'm not sure why this pen. It's like it doesn't respond fast enough. So this is negative 36K minus, and this is K squared minus 132K. And then plus 12 times 120 is at 1,444, 440. Has got to be greater than or equal to 0. So let's see, that's K squared. And this becomes minus 96K minus, or plus 96K minus 1,444 has to be greater than 0. And if you solve for the roots, I believe, unless I made a typo, you get that one there. And the reason why this one is because this one right here tells you that K has to be greater than 120. Well, that doesn't work for us because if this is a tighter requirement, then that's why we would limit it to those values. So solving for the roots of that is how we would get that. If I did that correctly, I might have made a typo about. And then this last one, K has to be greater and equal to 0. So it's just algebra. It's just doing the Ruth Horowitz and just doing algebra. Does that answer your question, Sean? I think that was Sean who asked that. We not. Okay. Other questions? So I'm not planning on covering any new material. I'm not feeling the best, but I want to make sure that you get your questions answered.
Just a quick question pertaining to the exam tomorrow.
Yep.
So I don't know if this has been said or not. Is it still going to be in person?
So you can do the option. You can do it in person, and Pascal's going to be there like he did the last time, or it's going to be available on Zoom. So Pascal, last time he kicked it off, and then I took over for him after I finished my lab. But I can't go to campus, so I can't. I'll try to jump into the Zoom, but he still has to proctor because I can't go to the live lab. So
Okay.
yes, that is available. You have to let me know by probably, I would say 8 o'clock tomorrow morning if you plan on taking the class remotely, taking the test remotely.
And my only other one is as far as the block diagram stuff. Will we be provided that table or
This one right here?
during the exam or no?
Yes, I can provide it.
Okay.
I will bring that.
All right. Thank you.
Sure. Anything else? Well, like I said, I'm not feeling great, and I'm not going to present any new material. So if that's all you have, good luck.
Paul,
And
the
go ahead.
table you're talking about is the block diagram table.
Yes, it's this one right
Okay.
here. Okay, well, if there's nothing else, again, I apologize, but COVID kind of threw me for a loop, so it's not been fun. All right, well, if there's something else, have a great day. Good luck tomorrow, and hopefully I will see you in person next week. Take care, everyone.
Thank you, Paul.
Thank you.
Paul.
Paul. Hope you